Welcome everyone to the second session on proofs. We have four very interesting talks lined up. The first one is on batching adaptively sound snarks for NP, and Lalita will give the talk.
Thanks for the introduction. I'm Lali, and today I'll be talking about batching adaptive sound snarks for NP, and this is joint work with Brent Waters and David Wu. So since we've all heard a lot of fascinating things since the last proof session, let me quickly recap the notion of a succinct non-interactive argument, or snarg. A snarg allows a prover to convince a verifier that some statement X is an NP language L using some short certificate pi. The NP language L is fixed ahead of time in our model, and both the prover and the verifier have access to an honestly generated common reference string. We consider the usual notion of completeness, which is that honestly generated proofs with a valid witness are accepted, and the notion of computational soundness, which states that no efficient adversary can fool the verifier, that is, convince the verifier that a false statement is actually true. To make this non-trivial, of course, we want the certificate pi to be much shorter than the NP witness itself. In this talk, we'll also consider a notion of non-adaptive soundness, in which the NP statement X is fixed before the common reference string is generated. So what is the state of snargs? Over the last many decades, there's been constructions in idealized models, including the random oracle model and the generic and group model. We heard about some of these yesterday. There have also been constructions from knowledge assumptions. However, we really want to construct snargs from falsifiable assumptions in the standard model. We have the work of Sahai and Waters in 2014, which constructs a non-adaptively sound snarg for NP, assuming indistinguishability obfuscation and one-way functions. This, combined with the work of Jane, Lin, and Sahai in 2021 and 2022, which constructs indistinguishability obfuscation from falsifiable assumptions, gives us the first construction of a snarg for NP in the standard model from falsifiable assumptions. However, as I mentioned, it's only non-adaptively sound, so we might ask, what about adaptive soundness? Can we achieve adaptively sound snargs for NP? Before I talk about those constructions, I should address the classic result of Gentry and Wicks. This separation informally essentially states that no such snarg can exist, that there is no adaptively sound snarg for NP with a black box security reduction to falsifiable assumptions. So we may think, okay, so what do we do now? However, this claim does not rule out reductions which run in enough time to decide the NP language. One way to interpret this, which will be helpful for this talk, is that this means that the CRS for a language which is decidable in time t must at least grow with polylog t in order to keep the proof succinct. So with that out of the way, we can talk about the actual constructions of adaptively sound snargs for NP from falsifiable assumptions. After this being a holy grail for a long time, we have a flurry of work this year, starting with the work of Waters and Wu, which constructs an adaptively sound snarg for NP from indistinguishability obfuscation and one-way functions, as well as some algebraic assumption. They have a couple of different ones in their paper that they use to instantiate a re-randomizable one-way function. We also have the work of Mathiaraga and Peter and Vaikuntanathan, which shows that the Sahai-Waters snarg is adaptively sound in the designated verifier model. I'll talk more about the snarg in a couple minutes. We have follow-up work by Waters and Zandri, which relaxed the algebraic assumption that's needed in addition to IO and one-way functions. And finally, work by Waters and Wu, which completely removes this. So now we have an adaptively sound snarg from simply IO and one-way functions. However, one thing to note is that in all of the above constructions, the CRS grows with the size of the NP verification circuit for the language. So of course, we might ask, can we get a better CRS size? Can we get a shorter CRS? I say short-ish because we will not be able to achieve in this talk a fully short, that is like poly-lambda size CRS. However, if we consider the case of batch NP, that is deciding whether M statements x1 through xm are all in some language L. If we think about the NP verification circuit for this batch language, this essentially consists of M copies of the NP verification circuit for the language L, and some AND on top of all of these. So the NP verification circuit for batch L has size about the size of C times M, where again C is the NP verification circuit for a single instance for L. That means that if we use any of the existing constructions of adaptively sound snargs for batch L the CRS size will grow with the size of C times M. However, the Gentry-Wick separation only tells us that the CRS needs to grow with polylog M times T, where T is the time to decide a single instance for L, so the time to decide for all is M times T. So of course, the natural question is, can we get this M down to a log M? Can we get an adaptively sound snark for batch NP, where the CRS grows with the size of the circuit C times log M, rather than the size of the circuit C times M? And in this work, we resolve this question affirmatively. We prove the following theorem, that there exists an adaptively sound snark for batch NP with CRS size poly lambda, the size of the circuit C, and log M, where again, C is the NP verification circuit for a single instance for the language, and M is the number of instances. And the proof size is poly lambda, where lambda is a security parameter. Our construction uses sub-exponentially hard IO and one-way functions, as well as a re-randomizable PRG, which I'll talk about at the end of the talk. And we instantiate this re-randomizable PRG from the decisional Diffie-Hellman assumption. We have another proof of this theorem in the paper, assuming IO and one-way functions and a homomorphic re-randomizable one-way function, which I won't talk about in this talk because it's less generalizable than the construction from the re-randomizable PRG. So to give a little bit of a picture for where the ideas in this work come from, we start with the template of Sahai and Waters for a non-adaptively sound snark for NP. Building off of this is the work of Garg, Sheridan, Waters, and Wu in 2022, which constructs a non-adaptively sound snark for batch NP with a short-ish CRS, so the same parameters as the theorem I mentioned, just only with non-adaptive soundness. There's then, of course, the work of Waters and Wu, which gets an adaptively sound snark. And our work can be seen as taking some ideas inspired from Waters and Wu to show how to make GSWW itself adaptively secure. So let me begin by describing the Sahai-Waters template. Essentially, we should think of a snark for a statement X as being a privately verifiable signature, or MAC. The CRS contains two obfuscated programs with the MAC key K hard-coded inside. First is the prove program, which the prover will use, and this will sign a statement X if given a valid witness W. And second, we have a verify program that the verifier will use, which checks that the snark pi is in fact a valid signature for the statement X. So to write this out slightly more formally, the prove program takes as input X and W and runs the NP verification circuit and outputs a signature if the NP verification circuit outputs 1. The verify program checks that the signature was valid. A couple of things to note about this. First of all, this is why in all of the existing constructions which build off of this template, the CRS size has to grow with the size of the NP verification circuit, because the CRS contains an obfuscation of a program that includes a copy of this circuit inside. Another thing to note is that I've written this for simplicity as simply checking that the signature pi is in fact the correct signature. However, to do an easier security analysis, you actually do a slightly different check, either that a PRG or a one-way function outputs the same value on the signature pi, as well as what should be the correct signature. I won't have time to talk too much about the actual security analysis in this talk, but you can obviously see everything in the full version. So again, what if we try to just directly use this template for batch NP? Now our proof program is taking in all M statements and all M witnesses. While the proof, which is just a signature, is still short, the CRS size will grow with the size of the circuit C times M. And again, in this talk, we're really trying to get this M down to a log M. So to do this, we take this idea from GSWW to batch via chaining. So instead of having the proof program take in all M statements at a time, it'll only take in one statement at a time, but it'll also check a previous proof. So for the first instance, we don't need to check a previous proof, so the prover simply puts in X1 and W1 into the proof program and gets some proof pi 1. But from this point on, the prover will now feed the previous proof pi I sub 1, I minus 1, into the proof program when generating the signature pi I. And so on and so forth until finally the prover is left with the signature pi m, which will be the signature for all M statements. Of course, it might seem like the signature pi m is actually unrelated to the previous statements. In the real scheme, the prover is actually signing hi, where h is some hash of all the statements and I is the index. I won't get into this for the sake of time. And the proof algorithm will also be checking openings to this hash value. But essentially the idea here is that the obfuscated program in the CRS includes only one copy of the NP verification circuit, and the prover runs this program m times, rather than having m copies of the NP verification circuit in the proof program that the proofer only runs once. Of course, the hairy part is achieving adaptive soundness. All of the security analysis in Sahayan Waters and in GSWW heavily relies on the fact that we know the false statement in advance before we generate the CRS in order to do basically punctured programming tricks in the proof program. I won't get too much into the details of WW, but one idea from there is to use exponentially many hybrids to essentially do this non-adaptive soundness analysis for every possible statement one by one. In their work, they use a re-randomizable one-way function, as I mentioned earlier. In our work, we need a re-randomizable PRG in order to make this idea work with the chaining approach from GSWW. So in my last couple minutes, I'll just define and construct this re-randomizable PRG from the decisional Diffie-Hellman assumption. So what does this DDH-based re-randomizable PRG look like? Essentially, it maps a value z to g to the z, h to the z, where here we have z living in zp star, and g is a generator of a cyclic group of order p. To re-randomize some output y star in the domain of the PRG, which consists of y1 and y2, we simply sample a uniform r from zp star, and we exponentiate both values. So we output y hat, where y hat is equal to y1 to the r and y2 to the r. Note that this is perfectly uniform within the domain of the PRG. It's necessary that this re-randomization process is statistical rather than just computational because of the fact that, as I mentioned, we're doing exponentially many hybrids, and we will be relying on this re-randomization property in each of these exponentially many hybrids, which means that simply having, if we just had a computational property here, we would run into some issues with succinctness, and we need this re-randomization property to be statistical, though we still only need computational pseudo-randomness for the PRG. So it follows from the decisional Diffie-Hellman assumption. The second thing to note is that if and only if this output y star was in the image of the PRG, so was PRG of z for some z and zp star, that is y1 is equal to g to the z and y2 is equal to h to the z, then our re-randomized value is going to be then g to the zr, h to the zr, which means that the re-randomized y hat is also in the image of the PRG. So essentially here, the properties that we need from this re-randomizable PRG is that it is, of course, a PRG, that it has this statistical re-randomization, so a re-randomization looks uniform within the domain of the PRG, and that it maps the image of the PRG to the image and things not in the image to things not in the image. So again, to summarize, in this work, we show that there exists an adaptively sound snark for batch NP with CRS size poly lambda, the size of C, which is the NP verification circuit for a single instance for the language, and log m, and proof size poly lambda. And our construction uses I/O, one-way functions, and the decisional Diffie-Hellman assumption. So to talk about some future directions, we might ask if we can get a short-ish CRS for languages beyond batch NP, such as threshold or monotone policy batch NP. We might also ask if we can build an adaptively sound snark without the need for this algebraic assumption, like in WW24B, where they remove the need for this and build an adaptively sound snark from simply I/O and one-way functions. We might also want to construct these primitives like re-randomizable PRGs or homomorphic re-randomizable one-way functions from other assumptions. Thanks. Please look at the full version for all of the security analysis that I skipped, and I'll take questions.
Thanks for the talk. Quick question. So you said you have to prove things about like the hash with the number of the statements. So do you need collision resistance for that?
In fact, the hash will be a somewhere statistically binding hash, and we move around where it's binding.
Did you try to turn this construction of the I/O into an argument of knowledge? And if yes, are there any fundamental issues preventing us from reaching an argument of knowledge from I/O?
Well, so this is a fully succinct batch argument in the sense of like the proof is only going to be poly lambda size and will just be a signature. It's not going to have any sort of extractability properties like many other batch arguments, including the ones that we'll hear about later in this session, where you can actually extract one NP witness. In fact, this is zero knowledge. It's a zero knowledge snark. So I don't think that there's, you'd need to add probably other machinery and also lose some succinctness in order to have any extractability.
We have time for maybe one more question.
Sorry, just maybe syntactic question. So you cite Gen 3 wins as one of the barriers that you overcome, but once you use sub-exponential AO, doesn't it already kind of, so all this stuff about batch NP is kind of irrelevant. Once you use sub-exponential, there are no barriers, right?
Sure, yes.
Okay,
I mean,
just-
all the known, the JLS constructions have reductions that run in time that's exponential in the input length. So yes, we do have
No,
reductions.
this is a
there.
fantastic result. I just wanted to make sure that, yeah, okay.
Yeah.
Makes sense.
Okay, let's thank Lalita. And can we have the